Can you build a roof before the foundation? You can't. You must build a house step by step. First, you pour the foundation, then you raise the walls, and finally, you add the roof. Each step depends on the one before. You cannot skip ahead or rearrange them. Building a house is a sequential process. Each new step builds on past progress. Exactly the same thing happens in language. Can you understand the meaning of a sentence if you forget the beginning halfway through? You can't. Traditional neural networks don't get this, but recurrent neural networks fix this by processing the input sequentially, just like building a house. They take one word at a time. They remember what came before because they have a memory called the hidden state, and they build meaning progressively. Let's train a recurrent neural network to predict the next word using the following sentence. I am building a new house. This is the ChatGPT input, and we can use it to see the prediction while we are typing a sentence. The word I in the input goes to the hidden layer, and the output predicts the next word, which could be am or something else. At this phase, the model doesn't know much about the sentence. During training, the output is compared to the true next word. The word am from the output is compared with the real word am from the input, and it is correct. The hidden layer with the word I is passed to the next hidden layer. The previous input is not directly reused, but its effect is stored in the hidden state and passed forward. Recurrent neural networks updates the hidden state with each new input. It's like a person reading a sentence word by word. They don't reread the previous word, but remember their meaning as they read the next one. At each time step, the recurrent neural networks receives two things: the current input, a word in a sentence, and the previous hidden state, essentially what the network has learned so far. The next input am is passed to the hidden layer, and the output predicts wondering, interested, and the output is compared with the real next word building using a loss function, and we can see that the prediction is wrong. The model uses its own predictions to help build a context for understanding and predicting the next elements in a sequence. The model makes predictions based on the context accumulated up to that point. It updates its internal context, the hidden state, regardless of whether the prediction was correct or not. At the next time step, it uses this new context to make a better prediction. The resulting error from loss function is used to update the model's weights by using backpropagation. Weights and backpropagation can be seen as two smart supervisors on the construction site, which is recurrent neural networks. Weights are the rules. They decide how to combine the bricks, which are the inputs, at each level. For example, if the house has a wide door, ensure the frame is reinforced for extra strength. Backpropagation is the supervisor who corrects mistakes. They look from the roof down and inspect each construction step. Then they go back to the rules, which are the weights that caused that mistake, and adjust them a little. In conclusion, weights are the construction rules that get better with time, and backpropagation is the supervisor who learns from mistakes and fixes the rules. Let's go back to our sentence. The next input, building, is passed to the hidden layer, and the output predicts a my. This word is compared with the next real word a, which is correct, and so on. Short-term memory is the main limitation of recurrent neural networks. Recurrent neural networks can only remember recent information. As the sequence gets longer, for example full sentences or paragraphs, the hidden state forgets earlier context. For example, Maria put the book on the shelf, later she went to the kitchen. The recurrent neural networks struggles to remember that she refers to Maria because the detail got lost over many steps. This limitation is related to the vanishing gradient. The vanishing gradient is like an ice cube melting. If you are passing an ice cube through a line of 30 people, each person holds it briefly and their warmed hand melts a bit of it. By the time it reaches to the last person, it has completely melted. During training using backpropagation through time, the learning signal, the gradient, is multiplied over many steps. If the gradient is less than 1, it shrinks rapidly, eventually disappearing. This makes it hard for recurrent neural networks to learn long-term dependencies. This is when long short-term memory introduces a separate cell state acting like a long-term memory track. It uses 3 gates to regulate the flow of information. Forget gate decides what part of the previous memory should be forgotten based on the current inputs and the previous state. Input gate decides what new information to add to the memory, considering the current input and the previous state. Output gate decides what part of the current memory should be passed forward to construct the hidden state which will be used for prediction. Gated recurrent unit is a simpler and faster alternative to long short-term memory. It merges gates and uses only reset gate and update gate. It's faster to train and works well when sequences aren't too long. You can use recurrent neural networks for building chatbots, text generation, stock prediction, voice recognition, language translation, weather forecasts, video processing like video captioning, and text sentiment analysis.